Hello everyone and welcome to today's webinar on part 2 cable for location by underground infrastructure and tools. My name is Sanjay Yadav and I'll be hosting this session today. Speaker for today's session is Mr. Marcel Bird, who is a cable sales manager, and Mr. Henning Oidjin, who is a product manager for cable at MEGGER. Also on the panelists we have Mr. Mohammed Saleh, sales engineer technical at MEGGER Middle East, who will assist for the Q&A session at the end. So before handing the mic to Mr. Marshall, I would like to highlight a few points. You all are being muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in the chat window. All questions will be answered at the end of the session. We also have a page on Megger page on Facebook and LinkedIn. I'll just share that in the chat window so that you can go on that link and you can follow us for regular updates. We have upcoming webinars in March and April, so you can go on this link and you can register yourself for the upcoming webinars. There will be a small survey form at the end of the webinar, so please do fill the same regarding the feedback. The recording will be sent to you in 2 working days through the GoToWebinar system as a standard process. I now hand over the control to Mr. Marshall, so let's get started. Over
Brief
to you.
overview of our seminar today. Thank you for joining us today, Marshall.
Thank you. Welcome to the webinar. And I'm Marshall Bird, and so I will present a portion of today's best practice session. And then as Michael explained later, Henning Ochen will also do part of the presentation. And before I jump into the agenda, I would just like to make a comment that we're going to cover a lot of material during this presentation. And because of the width of material, we won't necessarily go into great depth. But anything that we don't reach in detail, you can always reach out to us later and ask for a tailored, customized webinar presentation specifically for your needs. Well, let's go ahead and get started. Today's agenda, first, I'll talk a little bit about medium voltage cable types. We'll talk about the different types of construction and how this applies a little bit to cable fault locating. We'll look at common underground infrastructures, and this is important because different infrastructures require different techniques and different tools. We'll talk a little bit about cable fault failure mechanisms, how these underground cables can be damaged and how they can fail. And then we'll talk a little bit, a quick review of some of the common cable fault locating tools. And after this short introduction, then we'll hand off the presentation to Henning, and he'll dive into a little bit of detail on some three-phase industrial circuits, networks, branched manhole systems, and some of the tools and techniques specifically for those type of infrastructures. And then at the end of that, we'll have a question and answer session. And after the question and answer session, I'll pick back up and I'll go over some URD fault locating infrastructure, and again, some of the techniques and tools used. And then we'll finish up with a final question and answer session. So let's go ahead and get started. We'll look at medium voltage cables, and you'll notice medium voltage shielded cables. So what we're talking about for most of this presentation is a shielded cable. And the reason that's important is because many of the techniques that are used for fault locating are specific to shielded cables. And in the North American market, these shielded cables commonly come in at 15, 25, or 35 kV class ratings. And if we just basically go through the cable itself, we have a conductor, copper, aluminum, covered by an inner semicon, and then we have the main insulation. And the insulation could be EPR or XLPE. Those would be the common extruded insulations that we would see today, followed by an outer semicon, and then of course the shield, the neutral concentric itself, and then the jacket. And these medium voltage cables come in different construction types. We just talked about the single phase shielded medium voltage cable. But you could also have a 3-core conductor where one cable has 3 conductors in it, and each of those individual conductors has its own shield. And then if you look down at the bottom of the screen, you'll see a belted cable. It looks similar to the 3-core. We have 3 conductors, but there's only a single common shield. And when Henning goes into his presentation, he'll probably dive into a little bit more detail on these different construction types. And as mentioned, EPR and XLPE are common installations that we see today, but there's still quite a bit of paper-led insulated cables out there. And the reason I kind of highlight that with these 2 pictures is these cables have been around for a long time. They're still out there, and they do require some different techniques and troubleshooting applications versus the solid dielectric extruded cables. All right, let's look a little bit about, or talk a little bit about underground infrastructure. When I was preparing this presentation, I found this interesting drawing from back in the early 1900s. Shows an intersection. I believe this is in New York somewhere, Broadway and Fulton. But even back in 1890, there was extremely complex underground infrastructure. And of course, this has a huge bearing on the type of tools and techniques that we use. So if we look at underground infrastructure, we can kind of roughly break it into 2 different areas, what we would call, a networked, a branched, a manhole system. I commonly call these systems, downtown network systems, and they come in different flavors, but some of the things that are common in these type of systems is the complexity. A network, a branched, a manhole system. Here we have on the right-hand side, or the left-hand side, a picture of a multiple conduits and cables. It can be a very complex environment. And if we look at the picture on the right-hand side, even in a trench environment where we've exposed some of the underground infrastructure, it can be extremely complex. Lots of different utilities. You could have all different combinations here. Then if we move to a URD system, in some sense, these underground infrastructures can be a little bit simpler, perhaps characterized by the classic green pad mount transformer in someone's front or backyard. If we look at some very simplistic diagrams of these URD systems, you could have something as simple as a simple loop feed, which is relatively easy to troubleshoot and to move the normal open for power restoration. However, the URD systems, they can get somewhat complex. Over on the right-hand side, we show a more of a radial design with kind of a tap or a branch configuration. So the URD systems, while in general they're simpler, they can have some complexity to them also. One of the other ways we can divide URD systems is whether it's direct buried or some form of conduit. And this has implications for troubleshooting and fault locating. If we have a direct buried cable, when we talk about fault location, what we mean is we pinpoint the fault, we dig up the faulted cable, and we repair it by putting a splice in. If we have a conduit system, in most cases, you isolate down to a section and you pull and replace. You pull in a new section of cable. Okay, so if we move on to some cable fault types, the failure mechanisms in medium voltage cable. And this slide, we use this slide a lot when we talk about test and diagnostics on how you can examine a cable, but it also applies to how cables can fail. And so we can start with, termination, a pothead, and elbow. Many times, if the termination fails, it can be traced back to a workmanship issue. And if we look at joints or splices, kind of the same thing. When we take new cable and we put a splice in it, when we work on it, if the splice or termination isn't assembled exactly to manufacturer specs, we might introduce a weak spot in that termination or splice that will eventually lead to a fault. We can also have weak spots in the cable itself, and these type of weak spots that you could have a manufacturer's defect right from the manufacturer. That's not very common in today's high quality cable, but it could happen. We could damage the jacket or sheath when we install that cable. And if we nick or damage the jacket, we could have water ingress, and over time that could lead to a fault. And again, when we pull in the cable, we could exceed the bending radius, or we could over pull it, so we could cause some type of mechanical damage. So if we look at these failure mechanisms, we're talking about workmanship, installation, mechanical damage, this type of thing. Then if we look at the insulation itself, over time, the insulation itself can degrade and fail. And when we dive into this, we talk about water treating, aging of the insulation on the solid dielectric cables, on the older PILC style insulate. The cellulose itself, the paper, can degrade over time. So long story short, there's all different ways that a cable can fail, many of them related to workmanship. And I guess just as a side note, we do use this same slide when we talk about test and diagnostics. And many of these types of failures, there is possibility to discover them with some type of test and diagnostics. So that does play a part in maintaining your cables. Okay, so if we move on to some equipment, one of the most common pieces of equipment that you would use in troubleshooting cables would simply be a cable locator, cable tracing, cable location. And in its simplest terms, you have a transmitter that injects a signal onto the cable, and then you can trace that signal in the ground with a receiver. And this helps to verify cable path, and that can be very important in a troubleshooting and fault locating scenario. Another important piece of auxiliary equipment, if you will, is the cable identifier. This device allows you to select a particular cable amongst many. So maybe you have an open trench with 3 cables, and that's what the top of the picture shows. And we can put a clamp, a sensor around each of those exposed cables, and one of them is going to have the signal that we're looking to identify that particular cable. If we look at cable thumpers, when most people think about cable fault locating, this is what they think about. They think about a thumper. And so this is kind of the core tool, if you will, that is commonly used for many types of fault location. And of course, thumpers come in all different sizes. Here we're showing some medium size to large systems. Over on the far right-hand side, we have a little baby thumper. And we'll talk some more about these thumpers. But one of the key things about thumpers today is when we start talking about fault locating sequences, some of these thumpers have built into them a fault locate sequence to help the operator move through and find the fault quickly and efficiently. And the earlier slide showed portable thumpers. There's versions of these that can also be mounted in a truck or trailer. The picture on the left-hand side shows a fairly large thumper mounted up into a trailer. You can see the radar up above it and a fairly long cable reel on the right-hand side. And then the picture on the right shows a truck mount thumper that's not yet installed. It's being prepared to be installed into a truck. Other piece of very common equipment is a TDR. We're showing the display screen here of a TDR. The radar, the time domain reflectometer, this tool is used to get a distance to the fault, a distance to the end of the cable. Sometimes you might get distances to splices or transformers, but basically this is your, excuse me, this is your distance device to help you identify, to pre-locate where the fault is down the cable path. And also on the right-hand side is a pinpointing device. Now, I'll commonly call this a listening device, but that's really not correct. It does have a headset, and with a headset, everyone recognizes, oh, I can listen to a fault. But a modern pinpointing device does much more than just amplify sound in the ground. If you look closely at the display on that, it says 66.7 milliseconds. That's how far away the operator was from the fault. So this can basically give you a distance to the fault, and we can display that in either how long it took the sound to get to you in terms of milliseconds, or if you want, you can even put that into a footage measurement where it'll tell you how many feet away you are from the fault. And then let me finish up in terms of equipment with an example of an integrated test van. And an integrated test van, I use the term integrated to indicate it has fault locating equipment in it usually. So it would have a thumper, a radar, and you could have the auxiliary equipment off to the side in the van. But many times these vans also have test and diagnostics equipment. So you would have potentially a VLF, a partial discharge, a tan delta. You could have some combination of these test sets side by side with the fault locating equipment. And this is important in the overall scheme of things. Rather than just troubleshoot and repair the cable, you have the option with an integrated system to also do some diagnosis, determine what type of condition the insulation is. Are there any future problems with terminations, etc.? And as you go through the test and diagnostics routine, if you have a cable that fails under test, you have the fault locating equipment to quickly figure out exactly where the problem is. Okay, so that's just a quick review of the equipment, and I'm going to pause here and we're going to switch it over to Henning's presentation where he's going to dive in a little bit further on the underground infrastructure.
All right, Henning, I'm going to send control over to you right now. You ready?
Yeah. Oh,
All right, here we go.
okay. Okay, so thank you for attending this this webinar. We call this a best practice seminar, and it's a little bit different than our typical webinars because a best practice seminar is really there to give you an overview over the state of the art of different technologies and methods. And so it is, like Marshall was already saying, not necessarily always in depth in every detail. So what we like to encourage is if you have certain questions afterwards, or you like to explore certain topics in more detail, we are very glad to provide another, let's say, maybe more detailed webinar, specifically custom to what you would like to discuss. So when we look at, and I'm looking at the three-phase scenarios here, and so we have basically two types of three-phase scenarios. One is what I would call the three-phase high-load industrial circuits, which also includes wind farm circuits. And these are typically characterized by, the industrials, maybe 2,000 to 5,000 feet. The wind farms can go much larger, much longer, maybe 50,000 feet. And most of the time, all these circuits have either XLP insulated cables or EPR insulated cables. There is very little paper cable involved in these industrial circuits. Typical system voltage is 35 kV, and typical conductor sizes range from 350 to 1000 MCM. Could be also maybe sometimes 1200 or 1500 MCM, depending on the load. So when you look at what this really does, is the length of the cable and the conductor size affect the cable capacitance, and that is one of the parameters we need to understand when we do fault locating later. So the cable capacitance on these cables per phase is typically between maybe half and 5 microfarad. Half is the shorter ones, and 5 would be a long wind farm type cable. Most of the time in these type of circuits, the cable segments can be isolated, and that is very important because when I have isolated segments of cable, my fault locating procedure is becomes a whole lot easier compared to when I have one piece of cable that is, like we had in one particular incident with one wind farm, was 26 kilometers long, right? And then fault locating becomes very difficult. So on the next slide, I show you just very briefly a circuit diagram of a three-phase. You see here the three-phase on the left side, and then you see branching off the three-phase, some single-phase, and so on. But the important thing is that these can be isolated. They are either switchgear or typically involved, so it can be all isolated, and that is very, very important. And on a side note, the old wind farms, some of the old wind farms, they couldn't be switched around. They had all T splices in them, and it became a nightmare to fault locate. And today in wind farms, we typically have sectionalizing or switching cabinets also, so to make that aspect a whole lot easier. And the most important thing, fast, much faster. Okay, so whenever we do fault locating in three-phase systems, we have to pay really attention to make sure that when we fault locate on one of the phases, that the other two phases, if they are energized, they don't backfeed unknowingly somewhere into the phase that we want to fault locate. So there has to be some checking done to make sure that if there are any backfeed points, that they are open. Okay, so when we do fault locating, it's always good not just to go out and hook the thumper up and pray for the best. It's good to do some screening. And so what can we do in terms of screening to learn more about the type of fault we have? Because in the end, the type of fault determines what fault locating method will work best to find that fault and to find it in the quickest possible way. So one of the tests is we perform a insulation resistance test, let's say maybe at 5 kV, each phase to ground. And so we analyze the results, and look for that the results will fall in 3 different categories. Either we have a fairly high insulation resistance, and high, I'm saying above 100 megohms. That would typically indicate a good insulation resistance. Even some of the solid dielectric cables, they could go much higher. But so this is on the lower end really of the solid dielectric cables. But what we have to keep in mind, even a high reading doesn't mean that this cable is fault free. Because remember, we're only testing maybe at a 5 kV, we have a 5 kV insulation resistance tester. So all we know is that at 5 kV, it has a good insulation resistance. So to really, when we get a high reading, we must afterwards perform a high pot test on that same cable, and we must perform it at the peak of, at least at the peak operating voltage. And what that means is if I have, 35 kV circuit, 20 kV phase to ground, that's RMS. So if I only use 20 kV DC to high pot, it's not going to be good enough because my peak voltage is 28 kV. So I have to at least test up to 28 kV DC to see whether that cable has a issue. And even then, if that turns out to be good, it's not the ultimate answer whether the cable is good or not, because if I had an open conductor, I could even have a much bigger gap, which would require even a higher voltage than the phase to ground. The phase to ground voltage, peak voltage, is only good for basic pinhole faults. They will find those, or they will indicate that I have that type of a fault. But if I have an open conductor, and you will see there is one other test that we will do in a moment that will then close the loop. And with that test result in, I can make a final decision whether a cable is good or not. So it is several steps involved. Many times, somebody does a insulation resistance test and reading the sign says cable is good. Well, it might be, but it could also not be. And so be careful about this. So the second category is when we have insulation resistances, maybe between, I'm using here 500 kilo ohms and 1 mega ohm. So that is typically indicating I have a high resistance fault, or basically what is a high resistance fault is a pinhole fault, and a pinhole is an air gap. So I have a flashing air gap, and that's why it's high resistance. So it builds up voltage to the breakover voltage of air, and then it flashes over. And then I have sometimes faults that are much lower in resistance, less than 100 kilo ohms, and I have seen faults that are maybe 2 kilo ohms, 5 kilo ohms. And when we have those type faults, we have to be very careful, because sometimes these faults will not flash over anymore because they have so much leakage current that it cannot build enough voltage up to really flash over. And the other issue with those faults is we might have to limit our thumb energy. And you might think that is a very strange thing to suggest. But why do we do this? Because if we have a fault that is very low resistance and I put dump enough energy into it, it could happen that I make that low resistance even lower to a not completely short circuit, but close to a short circuit, which then I will have a big issue finding pinpointing, because a short circuit fault is much harder to pinpoint than a flashing fault. So, but there are telltale signs as we go through the process that will suggest to us which way we have to go. And that is why it's so important to do some of the screening tests up front. Okay, so what I also can do is I can use the TDR, and you heard Marshall was saying the TDR is a distance meter, and that is what many people see as the benefit of a TDR, and that is certainly the case. But the TDR is in essence really not a distance meter by definition, it is an impedance meter. And it shows impedance, and it shows really impedance differences along a cable. A good cable would have no impedance change, so it's a flat line on your screen. And anytime you see some wiggle on the screen, that means it's either up or down. That means a higher impedance or lower impedance than what the characteristic cable impedance is. Many cables in these distribution cables are 50 ohm cables, and so if you had, suddenly a spot where you only have 10 ohms, you would see a downward blip. If you have suddenly a spot where you have maybe 150 ohms, you have an upward reflection. You still see the end of the cable, however. That is important, okay? So why do we do this? Because we can do, again, with a TDR, we can do a phase comparison. So we connect phase to ground like we would normally do, and we can compare the three phases to each other. And what we're really trying to identify with that test is we're trying to find out whether we're really looking at the true cable end, because and that can be verified. We can do a absolute positive test to make sure we can see the cable end, because that excludes the other two possible findings, a short circuit and an open circuit. If we see the cable end, then we cannot have a short circuit and we cannot have an open circuit. If we do not, we cannot verify the cable end, then we might have a short circuit or an open circuit in the cable. And the distance to those is where that short or open circuit is located, which means there shouldn't be a open or short circuit in any of these cables. That means most likely that's where a fault is, okay? It's an indication, a first indication that there's something wrong with the cable if we cannot ascertain the true end of the cable. Okay, we can also do with the TDR a different comparison test, and that is a face-to-face test. Not the face-to-ground, but the face-to-face. And the face-to-face test on a three-phase circuit has one big advantage. What it will really tell us beyond any doubt whether we have somewhere an open conductor. If I do a face-to-ground test with the TDR and I get an open, it could be an open neutral, it could be a cut cable, or it could be a open conductor, one of the three. When I do the face-to-face test, I get an open. It can only be an open conductor, and that is very important to know when I thought, okay, I have an open conductor. Okay, so really what that test does, the face-to-face test, it measures the impedance differences between the phase conductors. And wherever there is an impedance difference, it doesn't have to be a complete open, it doesn't have to be a complete short circuit. Just a difference in impedance shows me that there must be a difference in the conductors. And whatever difference there is means there is some damage to the conductor, because if the conductor is fine, I wouldn't see that difference in impedance. So in a way, that difference in impedance between conductors is an indicator where most likely there is a damage or a fault, okay? And I will show you a slide here where you exactly see this, okay? This is was a 345 kV pipe type cable out of a power station, generating station. And it was so pipe type is filled with oil, three phases in the pipe, in the steel pipe, filled with oil under pressure. It had failed. And so when I tried many different things and couldn't really make ends meet. And then I said, okay, let me do the phase comparison, okay? And you see here on the right-hand side, you see the big open. So that was the end of the circuit. Actually, the circuit went out underground from the power station, up a hill on the switch yard, and then it went on overhead line out, okay? So it was about I think 8,000 or 9,000 feet underground section up to that switch yard. So when I did this phase comparison, you can see the green line and the purple line, right? And you see clearly there is a difference. And so the one is lower impedance than the other one. The other one is pretty straight, so it probably has no problem. But the blue one certainly has a problem because it's not supposed to have a different impedance here. So what we did is, this was the indication to start looking, and in this case, little luck on your side is always helpful. We looked on the map and we found that distance was the first manhole out from the generating station. So we opened the manhole and I said, well, let's try, maybe we can thump it. And we were lucky, it did thump, and it was right in the splice, in the first splice in the manhole. So I'm just saying, but the indication to find that spot was through the phase comparison method. It's a very powerful tool when you have a multi-conductor cables or multi-conductor circuits. Okay, so what are the typical faults that you have after going through the pre-screening? What are the typical faults we expect in three-phase, circuits with solid dielectric cables? It's pretty flash. For the most part, those are flashover faults, high resistance faults. Okay, and the most common fault locating method today is the in pre-locating that we do a pre-location in these circuits. And why do we do a pre-location? Because the pre-location gets us an approximate distance to the fault. And what it really does, it reduces the thumb time that we need when we have to pinpoint. Typically, once you have a distance from pre-location, your pinpointing shouldn't take much more than maybe a few minutes to really narrow it down to an area of about a square foot or maybe 2 square feet. So most circuits can be sectionalized by various methods. Okay, I mean, many of these circuits have fault indicators installed, so we have already a pretty good idea where to look. But we can also, and I think Marshall eventually will talk about sectionalizing method in URD loops. So I mean that same technique could be also used in some of these circuits. Um, and that allows us also, because most circuits allow us to isolate individual phases. That's very important because you will see the difference when we talk about network systems where that is not always the case. But in these circuits, we should be able to isolate individual phases, which again makes it a whole lot easier to fault locate. And so these circuits present really a point-to-point scenario. The TDR is a very good tool to apply to point-to-point fault locating scenarios. And that's what we have for the most part in these type circuits. So I will show you here the pre-location methods. We typically use two pre-location methods. One is what we call the arc reflection method, using the TDR. And TDR stands obviously for time domain reflectometer because it measures the reflections in the time domain. And that allows us with the velocity to calculate the distance. It's not a distance meter, it's a timing meter, so to speak. But no velocity, we can calculate the distance to the fault. So with the arc reflection method, we get at the fault a negative reflection because, when we put the high voltage on at the pinhole, we get a little arc. The arc shorts out the center conductor to the shield. And when at the very same time we shoot in the TDR pulse, the TDR pulse sees a short circuit and will show a negative reflection. That's what you see on the right hand picture here. You see the blue trace is just the TDR trace by itself, so no high voltage. It shows the end at 449 feet. And then in the second step, we do the same thing. We repeat it. We repeat it, but using also discharging the capacitor. It flashes over and it makes that TDR pulse reflect negatively. And where the impedance mismatch is, see, up to that point, the two traces are identical and they're split up, and that's our fault distance, 257 feet in this case. Now, so if you look at this process of arc reflection, we have to create a flash over first, and then we have to shoot in the TDR pulse, and everything has to happen at the right time. It has to be synchronized, so the TDR pulse sees an arc. If the TDR is too fast, then it will not see an arc because the arc hasn't developed yet. It doesn't see the fault. If we shoot in the TDR pulse too late, it can also not see the arc because the arc has already extinguished and we don't see it. So you need the synchronization. Sometimes for certain faults, but especially sometimes on paper cables, that is much more difficult to do. And for those situations, we have another method. We call it the ICE method or the current decoupling method, which is using a TDR, but not as an active TDR where we send out a TDR pulse. We're using merely the TDR as a transient recorder, like a scope. And so we use the thumper, we thump it, the cable at the fault, we get a flash over, and so we get now the flash over occurs between the conductor and the concentric neutral. So we basically getting a signal on the neutral, which forms a standing wave between the fault location and the capacitor inside our unit. And you can see on the left-hand side, you see it is this this curve, it's pretty much like looks like a, sinusoidal curve, but it's a curve that has repeated peaks in it, and the peaks all have the same distance, and the forward distance equals the peak distance. So we see here we have 735 feet, but like I said, because it's a standing wave between the forward and the capacitor inside the unit, we will have to subtract the test lead from that distance. If we have a 100-foot test lead, that means that fall is 635 feet out. So these are the two basic methods to do a pre-location for flashing faults. That's very important to understand. If I have a non-flashing fault, they don't work, and I need different method, okay? But for flashing faults, and in these type cables, like I said, solid dielectric cables, for the most part, we have flashing faults. These are the two typical methods being used today. Okay, so once we have established a pre-location distance, now we can do the pinpointing. And we do pinpointing clearly when this is a direct buried cable, because we need to know where to dig the hole. But even if we have cable in conduit, it is a very good practice to do a pinpoint, because it confirms the result of what the pre-location method did yield. And because I have, like Marshall was saying, typically I have to cut the cable, and I don't want to cut the wrong cable segment. So it's always good if you have a chance to verify a pre-location result with a pinpointing result. It's a very good practice, regardless whether in conduit or not in conduit or direct buried. So in this case, Marshall was already mentioning a little bit. What we strongly advocate as the best pinpointing method really is what we call the coincidence method, and we call it, in a more common term, lightning and thunder. And you all can relate to this very easily, because when you're in a lightning storm, you see the lightning, you start counting 21, 22, 23, 24, 25. You hear the thunder, you stop, and you say, okay, so it's 5 seconds divided by 5. That means it's 1 mile away. That's how this method works. So it basically measures the time for the sound to get to you, because the thunder, or in our case, when we fault locate, the electromagnetic pulse from the flashover will travel with the speed of light. We cannot even measure this. So but we can measure the speed it takes, or not the speed, but the time it takes for the sound to get to us. And so you can say this type of pinpointer is like a stopwatch. If you look at this gentleman down here on the far left side, where he says 66.9 milliseconds. So he has a stopwatch, and it has two sensors, the electromagnetic sensor and the acoustic sensor. And when it picks up the electromagnetic pulse, it starts the stopwatch. And when it picks up the acoustic, it stops the stopwatch, and it gives you the timing. And as he moves closer to the fall, obviously the time gets lower. So that's the indication in which direction you have to move. You have to move in the direction of lower numbers. And once you over the fall, you at the lowest number. And once you pass the fall, you see numbers go up again. It's a very simple principle, but it's a very excellent principle, because it doesn't rely purely on the sound. Whenever you rely only on the sound, there are many things that can go wrong, and it's not a very efficient method to just acoustically try to locate a fault. So with that, I like to switch now my presentation and go to the three-phase downtown branch network circuits. And again, a couple parameters of them: 5 to 20,000 feet, sometimes 40,000 feet. We're working with one customer has 100,000 feet, but that's out of the ordinary, right? But most of these circuits are in that range. And originally, because these downtown systems, they are the oldest systems. They are much older than any URD system because they go back to the end of the or early 19th century, right? So they are really old systems, and because of their really old systems, they have many times still paper cable in them. And when you have paper cables, Marshall mentioned already, there are two types of paper cable, belted and unbelted. Uh, and so the reality is, in many of these systems, you have a mix of cables. You have old paper, it could be belted, unbelted, or both, and you could have spliced in with EPR and XLP. So you have really a mix of different type of installations, and that's important to understand. And then we have conductor sizes typically. Let me just. Excuse me. This stupid MSN. Oh, I'm sorry. So we have no. I'm on the computer, but I cannot talk. Okay, so we have in these systems, like I say, a mix of different type cables, and 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 the voltage is typically only 13.2 or 13.8 in these systems, and so pretty much all these cables are 15 kV class cables. The typical conductor size is between 350 and 500. Sometimes you have also 1000 MCM. Again, it depends on the loads. And but what's really very different about these circuits is they have typical branches in them. And these branches, in many cases, cannot be isolated. They are hardwired T or Y splices. And that makes fault locating a totally different ballgame. In addition to it, we also have most of the network transformers that are used are delta transformers. And again, they could be hardwired or they could have switches in them. And I talk about that in a moment a little bit more. But whether they are hardwired or they have switches, again, makes a difference what we can do in terms of fault locating. Okay. And I had planned for a circuit diagram on the next, and you see only placeholder. Unfortunately, I was not able to secure that map, that circuit map, because of some uh, uh, proprietary concerns. So, but anyways, I think most likely any of you who have worked in downtown network systems, you know exactly what I'm talking about, and I will later show basically a rendering of my own on a system like that, but a much more simplified diagram. Okay, so so now what's really important is that we understand the type of transformer we have. And you see here, this is a board, underground board. You see the network transformers in them. And like I said, we have two types hardwired in the circuit. So it's always in the circuit when we're performing fault locating or also cable testing. Um, and that means the phases cannot be isolated from each other. And there are other systems, other transformers where you have three-way switches in them. And I try to indicate this here. You have 1, 2, 3 phase. You have here the delta transformer, and you have here the switches. And the switch has 3 positions. Obviously, an operating switch when the transformer is cut into the circuit, then you typically have a grounding position, and you have, and that's the most important for us from fault locating point, we can open the transformer. So if you see here in this diagram, if I open the transformers, now I have 3 individual cables, and I can actually fault locate on A phase, B phase, or C phase. If I don't have those switches, I cannot do that. Okay. Okay, so Uh, Interesting. Why isn't it moving? Okay, now it's moving. Okay. All right. So we need to apply some general considerations when we do fault locating on three-phase branch networks. Okay. One of the things is very important. Uh, when I say always, I never say always, always, but for the most part, you always want to start at the substation to fault locate, because that is from where the circuit was fed when it failed. So we look at the entire circuit from the substation going out to the multiple ends in that circuit, because a branch network system has probably, I don't know, 40, 50 ends basically, right? So another thing that's very important, all network protectors must be open, must be confirmed open, because I cannot have feedback from network transformers to the circuit I wanna fault locate in. Most of the time today that is done via SCADA operations. So in the old days, one had to go out to every transformer and make sure that the network protector actually opened. Okay. Then I have to look at the from going out from the substation. I normally have a, like, what we call a substation getaway, and that can be a cable that could run, maybe from a couple hundred feet, but could also be maybe 1,000, 2,000 feet to the first, let's say, either branch point or to the first network transformer. So it makes sense to look at that section differently, because that is a true point-to-point fault locate. And so I can use the same methods that we just described on the industrial type circuits. And that's the benefit of using a TDR for that portion of the network. And you have two possible outcomes. Either you find a fault in that section, then you home free, very good, and it didn't take much time to find it, or there is no fault in it, and that means you can exclude it. You don't have to pay any more attention to that long section of cable, and you can move on to the real branch part of the network. So that's, if the fault is in that branch network part, the TDR-based methods are useless. And why they're useless? Because, like I said before, the TDR is an impedance measuring device, so it measures impedance changes. Now you can see in a network, I have a lot of splices, and I have transformer terminations. I have all this stuff in, and every time this is associated with an impedance change. So I have a jungle of impedance changes, and because every impedance change really constitutes a reflection of part of the radar energy. That means if I have enough of those impedance changes and reflections, my radar pulse is running out of steam and I don't see anything anymore. So that's why typically we say in a branch network that the benefit of the TDR is very, very limited. I always say, maybe in 20% you're lucky, because if you just happen to have the fault pretty close to where your connection point is, you will see the fault. But this is not a method that is typically used. On the other side, to just try it takes you maybe 2 minutes to see whether you see something that looks meaningful. If it doesn't, you move on and you do whatever you do normally. Okay, so there's nothing lost. There's only something to be gained, because if you see the fault, the time savings is tremendous compared to a traditional fault locate in the branch network. Okay, so also what's important to recognize in these type of networks, we don't need to know the exact fault distance, because we're looking for the faulted cable segment between two manholes. So the distance is not that critical, and And so what's also important is obviously, if we can switch the transformers in that open position, we should always try to do that because that allows us to isolate individual phases in the system. Um, I just talked to a customer a couple of months ago, and they used to do that all the time, which made their fault locating very efficient, but at the expense of the time to make sure that the transformers were in an open position. And because they had a fairly old system, they had to basically go to every transformer and manually check that this happened. So management in the end decided it's too much of a time uh, loss of time. So we better off trying leaving transformers in and trying first to see, and only if we cannot find it, then we might have to do that step. So, there's always a compromise. It's always depending on what the specific situation is, what is the best solution. One other point that's really very important and sometimes gets a little forgotten is the bonding in these network circuits. In the old days, in every manhole where you had a splice, you had a grounding rod, everything was bonded, was perfect. Today, in many cases, there are no grounding rods anymore in the manholes, or they're abandoned or not replaced because they're so old. Uh, but why is bonding important? Because the method we will use looks for basically a current signal, electromagnetic signal, and and if we don't have good bonding, what could happen theoretically, just to make the point, is you sending a pulse out, it flashes over, and that same pulse comes back on the very same cable. So you have a pulse in one direction and a return pulse in the opposite direction. And when you measure the signal, you measure the difference between the two, and there is no difference, and you measure nothing. Now, you always will measure a little bit, but you can see it could be that you measure a very low signal, which makes it very, very difficult. So the better the bonding in the system, you eliminate this issue. And some of you might have used there's a unit in the market, it's a very nice unit. It's called the X35. It's an above the ground underground meter. You don't have to open manholes. You can pick up this electromagnetic pulse above the ground, but you can see that makes it very nice and convenient. You don't have to go in manholes. You don't have to pump manholes out and to do all this good stuff. But because you do it above the ground, the signal is already reduced. So you need a very high sensitivity signal unit, I mean, to pick the signal up. Now, if you have a poor signal, it could be that the unit won't pick up anything. And that's what I hear sometimes. People say, well, we use it, sometimes it works and sometimes it doesn't work. That is a clear indication of the bonding condition in your circuit. So I just want to point that out. It's not equipment. Every piece of equipment has limitations, and it's designed for certain things to do. Okay, so what is another screening test now? After we going through some of the considerations, what is a screening test we can do? Again, we can do a insulation resistance test just to get a feel for the insulation resistance, because really when we have a fault, typically we expect to get a low reading or a lower reading than a good cable has. But the fact is, if we know how low it is, it will tell us. If we have, let's say, in the extreme case, we would have a dead short, we would have no resistance, which normally doesn't happen. We always have maybe the lowest I ever saw was about 500 ohms. So that's low, okay? But if you have a high reading, that means you have a good chance to get a flashing fault, okay? So and the same things apply if you have a really low resistance fault. It might not sound, and if it still sums, you will be very careful how much energy you dump in that uh, in that fault, and not the old-fashioned way. Well, crank it up till you get more oomph. Okay, that might be just the worst thing you can do in that situation. So the insulation resistance gives you an indication where you are. Okay, Now we can also do, because I mentioned we have in these circuits many times we have paper cables, so we have belted or unbelted cables. And the belted cables, like I said, they don't have their own neutral on each conductor. So that's why we also do the insulation resistance not only face to ground, but we also do it face to face. Because if we had a face to face issue and we only testing face to ground, we might not see it. Okay, we might not see it. Sometimes you see it both ways. Okay, but again, you want to fault locating is a procedure where you want to exclude whatever you can exclude, because then in the end there's only one or two things left, so you have a good idea what the problem is. And so a negative result is also a very positive result in terms of fault locating. Okay, so when we do a face-to-face, again, the readings are very similar. You know, on paper cable, you know, paper has lower insulation resistance typically than solid dielectric cable. So you see, I lowered the number down to 50 megohms for a good resistance. Um, and so if you have a high reading, that means either you have no belted cable or you have no face-to-face problem. One of the two. Okay. Now, if you have a lower reading, face to face, that means there is something going on between the phases. But in addition, since we did the face to ground before, we also can look at the face to ground results and see whether that face to face translates also into a combination of face to face and face to ground issue. Okay. And again, if we have really low readings, then we have to be very careful how we, you know, in terms of how we apply energy to that fault. Okay, so when we another screening practice is, besides doing the insulation resistance face to face and face to ground, we can do now the same thing again with the TDR to measure the impedance differences. Okay, and again, it's for the face to ground. We do it for the same reason. We want to see whether we see the true end of the cable. If we can do it, like I said, in a network system, you have a lot of reflections. It might not work very well. I mean, all these TDR things I'm talking about right now, they might not work that well. But we can give it a shot, because if we see something, it's a very valuable result. Okay, and we can also do face-to-face comparison, like I was explaining on the industrial circuits, and but overall you have to keep your expectation low on using a TDR in these branch network systems. So it pretty much defaults back to the insulation resistance test. Okay, and just to give you one example, I had once a situation where, you know, customer was pretty yeah, I don't want to say desperate, but they were really trying to figure out. They had a fault in the network, and it gave them a lot of grief, and they had an issue to really go to the substation because it was very hard to reach. So they tried it from one of the ends, and but they were lucky because they were able to isolate the put the transformers in the open position. So they actually had three phases. So I said, okay, do an insulation resistance test. So they did it face to ground, and everyone was low. Everyone was low. And then I said, well, do also the face to face. Everything was low. So I said, that is highly unusual that everything is low. That means almost suggests that you have one spot where everything just completely blew up and is shorted out to each other. Okay. In the end, they went to the substation and they found, I think it's called a reactor that was right in the substation that had caused a short circuit between all phases. Okay. So that's why I'm saying the insulation resistance reading gives you a good indication, and the fact to go from the substation can save you a lot of time. Okay. So All right, so now, uh, what are the typical faults in these systems? Okay, typical is a blowout fault, pinhole fault, high resistance fault, which happens typically in the straight sections between manholes. And then you can also have obviously splice failures, okay, in the manholes, at the Y splices, at the T splices. And, typically in these manholes, you have a lot of water, it's not a very pleasant environment to work in. And the cable itself, the cable type, whether it's paper or solid dielectric, can also have an impact on the fault, and how to find it. Um, and uh, um, and like I said again, belted pay cables can show face to ground and face to face faults. Okay, and you see here again this photo on the right hand side. You see a belted cable. You see each face has paper insulated, and then but not every insulation has a concentric neutral over it. There's only one concentric neutral. That is that copper tape that you see under the left sheath, which acts as the neutral. Where on the left side you see every face has its own concentric neutral. Now, obviously, this is not a paper cable, but it doesn't really matter. This is a XRP cable. Okay, now just to, probably you have all seen this, on the left side, you see a typical blow up in a manhole, and you see all this white tape. This is normally tape that's protection to prevent fires from catching onto other cables when one cable blows up. And it did a good job here. And then you see the congestion in the manhole that Marshall was already pointing out. So these are very complex manholes. And Marshall mentioned one tool. He talked about the cable identifier. That is sometimes a very, very important tool to even figure out when you're in the manhole, where's this cable coming from, where's it going to, right? So you're really on the right cable when you do your fault locate, okay? And then on the right-hand side, you see a typical manhole with a lot of water in it, okay? So most manholes I've seen, a lot of water. Okay, so what are the typical methods to fault locate? Um, we call it the current method, or in the more colloquial jargon, chasing the fault current. Because there's one thing about the fault current. Fault current will find the fault. We cannot see the fault current, so we have to find a method that we can detect the fault current, and that is what we use a galvanometer for. So by putting a coil on the cable, and when we thumb, we get a current pulse, and with the galvanometer, we can pick up that current pulse, and we see the direction in which we have to go. And so the idea is, I don't go to every manhole. I go only to the Y or T branches, open the manhole, put my coil on the on the on the cable that incoming to the splice, and make sure I see a signal. That means the signal is still coming into that splice. And then I put it on the two outgoing cables. And in one cable, I will get a signal, and in the other cable, I will not get a signal. So I know, okay, I have to make a 90-degree turn here because my fault current is going that way. And then you go to the next Y splice and do the same thing. So you leapfrog from manhole to manhole, but only those where you have Y splices. And that is some people don't like it too much because they think it's too time consuming. But I would say this, from what I have seen is, on average, you save time doing it. There might be sometimes you get really lucky and you can hear a fault with the second method that I call here out as the acoustic method. You can. I will not deny that. But many times I have seen the opposite, where you cannot pick a good acoustic signal up and you just scrambling and cannot make ends meet. So this method to chase the fault current is a systematic approach that will get you to the fault. So let's talk about that. And the good thing is it works for flashing faults or non-flashing faults. Even if I had a short circuit somewhere, when I put my thumb on, that current still goes through the cable. I still can pick that signal up. Okay, very, very important. because the acoustic method, if I don't have a flashing fault, I hear nothing. So I can forget about it. Aside from the fact that it's sometimes very hard to locate the acoustic signal. People go down in the manhole, they listen in the conduit, they try to really do all kinds of things. It's not a very, it's a hit and miss approach. I have to say that way, and it's not systematic approach. Okay, and it works only on flashing faults. And like I say, the TDR method for the most part is not applicable, but I always say try it first, because you can do low voltage TDR gives you impedance differences between phases, which, like in the example I showed you, gave me the indication where to look for the fault, which is very powerful. Or basically low voltage means it's non-flashing faults. Or if I do arc reflection, I can do flashing faults. But again, arc reflection is very, very difficult to do on these systems. So these are the three methods. And here's, my network diagram, and you can see there are quite a number of manholes in it and branches in it, and you can see the fault is there on the lower side between the two last manholes, and you can see the red framed manholes are the ones I have to analyze to see where my fault current is going. Okay, and so that is a way. It is very, very straightforward, and I get a good, even if I have the bonding is not so well, I still get a good signal because I measure the signal right at the cable. I have to put the coil onto the cable, which is on the other side the disadvantage, because I have to open the manhole, and typically I have to pump the manhole out, which can create some other issues. Okay, so that is the method to really the best method in terms of a systematic approach to find the fault. Okay, and you see here, two different devices, and you see the coil here. This is a device. We call it impulse detector, which picks up the the signal, and this is a coil, and you put it on the cable. This, you can adjust the gain on this, and on the right hand side you see the coil. This is purely a galvanometer, no battery unit. It's purely a galvanometer instrument that doesn't need any power. And you see what they call the tick on the needle, and you know which direction you go. It's the same on this one. Now, if I can gain up the signal, I can see a larger swing, but it's very dangerous, because if you change the gain as you go further out away from the location where you connected, you can create big issues for you that you're chasing the false signal. Okay, so typically we say once you set the gain at where your thumper is connected with the unit in the left, then you do not touch the gain anymore. Okay, because it just makes a small signal is better than the wrong signal. Okay, so all right, one other quick aspect of thumping and energy and noise and all these good things. Many of the old thumpers were network thumpers, were single stage thumpers. Many of them had a rating of 25 kV surging, and there might be 7,500 joule. And you can see this. This is a curve that is this blue diamond shape you see here. It's 7,500 joule at 25 kV. But you also see when you talk to people in the old networks, what voltage do you thump at? Normally people say, well, I don't want to really go much beyond 10 kV because it's only 13.8 and it's old, and I'm concerned I thump this cable to death, because you might have to thump longer time, right? Because it will take some time to fault locate, using this method. So, and you can see if I go down in voltage, I go to 10 kV. How many joules do I have left? Maybe 1,200 joules, right? So that's a big cry away from the 7,500 joules that the nameplate says. So 1,200 joules is much less. It's much less noise than what I would get at 7,500. But I cannot use 7,500 because it'll destroy my cable, right? So that's the old saying, the surgery was very successful, but the patient is dead now, right? So we don't want to do this with network cables. All right. So that's where, in contrast to it, today you have more and more multi-stage capacitor thumpers. And you can see you have here an 8, 16, and 32 kV thumper. And if you look at that, you see we have absolute less energy than at the 7,500 joule from that thumper. But we have 3,500 joule, but you can see we have 3,500 joule at 4 kV, 8 kV, and 16 kV and 32 kV, right? So if you look at where you typically thump, you have much more energy available and what does that energy do really? More energy typically makes a louder bang, gives you a better fault image if you can do arc reflection, and it gives you also a better indication on your galvanometer. It gives you more of a tick. And why does it give you more of a tick? The energy, you can say, is the same, but why does it make a difference whether I have, let's say, 3,500 joules at 16 kV or 3,500 joules at, let's say, in this case, I'm using the 4 kV? Because when you go to the next slide, that explains it. It's energy. The energy is the same, but if the voltage changes, something else has to change. Energy is watt seconds. Energy, watt seconds means volts, amps, seconds. It's like your kilowatt hours you buy from the utility, right? So it's electric power times time. Okay, and what the difference is, even the energy is the same, the time that the power flows is longer at the lower voltage. You can see here, if I go 8 kV, at 3,500 joule, I have 4.5 microseconds. And if I go with the big thumper, the big old thumper, 7,500, and I go to 8 kV, I have only 0.96 microseconds. So the flow of that energy is much, much shorter, and the energy is actually much less. Okay, so that is why a multi-stage thumper is normally advantageous to be used in these applications, because I can better adjust the energy that I want to apply to a safe voltage to operate in my network system. Okay, so maybe as a finishing slide, these are general performance recommendations for fault locating equipment for three-phase circuits, whether industrial or network type systems. The surge generators, which are an essential part of any fault locating equipment, there should be preferable multi-stage units, two-stage at least, 3 or 4 stage, depending. The surge voltages should be between 25 and 32 kV, but with multi-stage, so you also have, lower voltage stages. The energy should be not less than 1,500 joule, and 5,000 joule is a pretty good number to have, especially if you have 5,000 joules at maybe 8 kV or 16 kV. Okay. Burn feature, okay? Many people are swearing by burning faults, and there has to be a little bit of caution that needs to be applied, because if I burn solid dielectric cables, I normally shoot myself in the foot. Because what happens when you burn a solid dielectric cable, you set the whole insulation material on fire, which means it smokes away. And that fault will be afterwards, you will not be able to thump it anymore. So it's a totally different issue when I have paper cable, because paper cable, I have oil in it, and I need to lower the fault resistance so I can thump it And that means I have to burn the oil, literally burn the oil and make from the oil carbon. So I have no carbon, and carbon has a lower resistance, so I can thump the fault. So burning is a good feature when I have paper cables. And like I was saying before, it all comes together when I have a mixed cable circuit in a network, and I do the high pot because I get a high insulation resistance. I said you have to do a high pot, and if I get a high pot where it fails maybe 20 kV, that is not a plastic cable. That is, or not a solid dielectric cable. That is in the paper section. So if I know it's in the paper section, then I can also much more freely use a burn feature, because a burn will only occur at the fault location. Some people are concerned. They say, "Oh, so much current." Well, let's put this all in perspective. We use maybe a good burner has maybe 500 milliamps, maybe a 1 amp. We make some burners that can do up to 20 amps. But if you really look at that current is nothing compared to the normal operating current on these cables, okay? So the current itself cannot damage the conductor. But when you have a low resistance fault, it will do a lot of damage there, okay? And that's the whole intention. It should condition the fault so I can thump it, okay? All right, so going on here, moving on, when we go to the fault locating itself, to the pre-location, it's very clear an inductive type arm filter is absolutely preferable over a resistive type filter, because any resistive type filter will suck out the energy that the thumper provides. So I use a big thumper with a lot of energy, and then I put a resistive filter in, so I'm defeating my purpose. So it should be a inductive type filter. If I use a TDR, and like I say, I would always recommend in a network fault locating system to have a TDR. In industrial systems, you need it anyways for pre-location, but it should have a range between 25,000 and 100,000 feet, okay? And it should have a very simple phase comparison feature built in, not one where you have to, store and recall and overlap and do all this. Whenever you make it too complicated, people will not use these type of features. Even they're good features, but they're too complicated. And then last but not least, you need a good pinpointing device. And it should be the combination of electromagnetic and acoustic coincidence technology that will give you the best results overall for pinpointing. So I think this was my last slide. So I think we will go to
Question and answer session. I'll take it from here. All right, wonderful. So Henning's knocked out his presentation for our first segment, so we're going to jump into our Q&A session. You guys have been throwing some great questions our way, and I want to jump into them as soon as possible. We have a lot to get through, so the first one I'm going to ask is going to be directed towards Robert Probst.
So yeah, we are open for the question and answer session. So anybody has some question, you can just post it in the question box, and Mohammed Saleh can answer the same.
Thank you, Sanjay, and yeah, good morning, everybody. Just let me know if you have any questions, and then if I can answer it, I'll be happy to do that.
So we'll wait for a minute to. So, okay, it seems there are no more questions, Mohammed. So,
I think yes, we are open at any time, so they can send their questions uh, later on if they want.
yeah.
We are
So,
happy to help at any time.
yeah. So, thank you everyone for attending the session today. And I have just paste email you the Mohammed Saleh email ID. So if you have any query, do mail us at mohammed.saleh@megger.com, and he'll be very happy to answer you on the same. And looking forward to see you in the next webinar. You have the link in the chat section. You can go and register yourself and follow us on Facebook and LinkedIn for regular updates. Thank you once again, and see you and have a nice day.